Greetings, everyone. I am Miguel Jose Barlis, a student of Master of Science in Electronics and Communications Engineering. I present to you a research paper entitled Blind Image Deblurring Using Elastic Channel Priors by myself and Dr. Carlo Noel Ochotorena. Images captured by conventional cameras are easily affected by blurring that results from the movement of the camera itself or from the movement of the subject while taking the image. It may also be caused by focusing effects, whether it be intentional or unintentional misfocus. Blur is generally considered detrimental to the image quality and has motivated researchers to develop recovery algorithms to attempt to reconstruct the clear latent image given a blurry image. This recovery process is generally known as image deblurring. The deblurring process is inherently an ill-posed problem as the introduction of image blur naturally destroys information from the original image. This is particularly true in the case of blind image deblurring, where both the clear image and the blurring operator or the blur kernel are both unknown. Since there could be an infinite combinations of clear images and blur kernels that results to the same blurry image. Because of this kind of nature of the deblurring problem, different priors that are based on the natural properties of image are introduced as regularizers to solve the problem. A typical optimization model used by many techniques takes this form. The red term or the data fidelity term ensures that the observed blurred image is close to the recovered image when the blur kernel is applied. The green and blue terms are priors or regularization terms where gamma and lambda as their weight parameters. The green term or the regularization term on the kernel is generally straightforward and is often implemented as an L2 norm to ensure that the kernel coefficients are generally close to zero. The blue term, or the regularization term on the latent image, on the other hand, is substantially more involved as it dictates how a clear image should behave. For this very reason, researchers have proposed various priors that attempt to capture the natural properties of non-blurred images. A few notable existing intensity priors include the dark channel prior of Pan et al. 2016 that asserts that the darkest pixel in any given area in an image is closer to zero when the image is sharp. A natural extension of this prior comes in the form of the extreme channel prior by Yan et al. 2017 that proposes that the brightest pixel in any given area is close to 1, assuming a range of 0 to 1. A more recent approach uses a nonlinear expression formed by the ratio of the darkest and brightest pixels that is roughly analogous to the local image contrast by Ge et al. 2021. Apart from relying on intensity priors, other approaches also make use of image gradients by asserting that sharp images have stronger gradients by Chen et al. 2019. A patch prior that compares image patches with a set of primitive patches was also proposed by Sun et al. 2013. Some deep learning based priors were also tackled by Li et al. 2019 and Kai et al. 2020. Generally speaking, the various priors are differentiated in terms of computational complexity, interpretability, and how universally applicable they are across various images. For instance, priors derived from deep learning techniques enjoy relatively low complexity and good performance, but are difficult to interpret and build upon. Sophisticated techniques such as the nonlinear channel prior excel in performance but come at a high computational cost. A good middle ground is offered by intensity prior such as the dark channel prior and the extreme channel prior. A further simplification of the dark channel prior describes the darkest pixels of an image within non-overlapping patches. This is in contrast with the overlapping patches employed by DCP. The resulting patch-wise minimal pixels prior was shown to outperform the DCP both in terms of reconstruction quality and speed. Despite the improvements introduced in the patch-wise minimal pixel prior formulation, the said prior, much like its dark channel prior predecessor, assumes that dark pixels are uniformly distributed throughout an image. Having equally distributed dark pixels that yield a sparse dark channel is ideal. However, this is not observed in most cases. In some images that have an even distribution of dark pixels, only few dark areas are observed, as we can see in this photo. So, in this work, we address this limitation by selecting a subset of dark pixels from the image and introducing an elastic search for the nearest reference dark pixel. Here is our proposed elastic channel priors, and it introduces improvements in two ways. First, it reduces the number of reference points even compared to patchwise minimal pixel prior, which should have an impact on the speed of the algorithm. More importantly, it allows for a flexible search for dark and bright pixels that is not constrained by a fixed window or patch size, which should result to a sparser dark channel and a denser bright channel. So this approach can be divided into two tasks. The first task is a patch-based search for the darkest and brightest pixels to be used as references. For visualization purposes, located in the right side of the presentation, we will choose the dark channel side of the elastic channel priors. A trivial approach to selecting dark or bright pixels would be to simply sort all the pixel values and select the lowest or the brightest pixels. Doing so, however, would lead to redundant clusters of dark or bright pixels. In order to ensure that the pixels are still distributed throughout the image, the input image is first divided into fixed-sized patches. Empirically, it was found that choosing a patch size that divides the image into roughly 100 to 400 patches was sufficient. After that, each patch is then represented by the minimum or maximum values. This step operates like the patchwise minimal pixel prior. The set of all patch minima roughly represents a nonlinear downsampled version of the image. To further enhance the prior, only the lower quartile of the dark values are used to describe the elastic dark channel prior, while the upper quartile of the bright values are used to describe the elastic bright channel prior. These two elastic priors can then be used in place of the original extreme channel priors to form the elastic extreme channel prior. So the second task involves matching each location in the image with the nearest reference dark or bright pixel. While the elastic channel priors conceptually describes an elastic search for the nearest reference pixel, the prior itself is simply a collection of the darkest or brightest pixels. This implies that it is not necessary to map each pixel in the image with its corresponding reference pixel. But just to visualize the elastic dark channel prior, it will look like this. In practical images, this is how the dark channels of the dark channel prior, patchwise minimal pixel prior, and the elastic channel priors will look like. As you can see, the dark channel of the elastic channel priors are sparser than the other priors. So we evaluate the proposed algorithm on the benchmark dataset provided by Kohler et al. 2012. The said dataset contains 48 blurry images generated from 4 high-quality base images combined with 12 camera motion trajectories that are used to form a non-uniform blur. Using the said dataset, we evaluate the performance of the proposed algorithm relative to that of the closely related dark channel prior and patchwise minimal pixel prior techniques. The average performance of the techniques based on the peak signal-to-noise ratio metric can be seen in the table. From these results, we see an improvement in the average performance across the dataset. However, the average performance does not effectively capture the benefit of the algorithm. Here is the visual comparison on the first two challenging images from the dataset of color. From top to bottom are respectively the blurry 1, 8, and the blurry 2, 9 images. From left to right are the blurred image, the blurred image using dark channel prior, patchwise minimal pixel prior, and ours, the elastic channel priors. Here is another visual comparison on the second two most challenging images from the dataset of color. From top to bottom are respectively the blurry 310 and blurry 411 images. From left to right are the blurred image, the deblurred image using dark channel prior, patchwise minimal pixel prior, and ours, the elastic channel priors. In order to glean more information from the data, we look at the box plot with respect to the full dataset. In general terms, the three methods appear to perform equally as well. The patchwise minimal pixel prior has a slightly lower maximum quality compared to the dark channel prior and our proposed techniques. Interestingly, the baseline performance demonstrated by the elastic channel priors is substantially higher than that of the two methods. This shows a distinct advantage of our proposed method. In terms of computational complexity, since the elastic channel priors utilizes the same framework as the patchwise minimal pixel priors, these two are nearly identical in speed. Overall, the improvement in the reconstruction quality while maintaining complexity points to the merit of the proposed technique. So in this paper, we propose the elastic channel priors by addressing the limitation of previously intensity priors. We demonstrate that these priors are effective since the elastic channel priors are generally sparser than the original dark channel prior. We also show that the proposed algorithm is computationally efficient since the search for the closest reference pixels do not require the calculation of the pixel distances. The experiments performed on this algorithm demonstrate that it outperformed the existing state-of-the-art techniques. So here are our references, and thank you very much for listening.